Okay,
Yes,
welcome to KIAS Strength Seminar. Today's speaker is Professor Ramy Brustein from uh, Ben Gurion University, Israel, and
yes.
he'll be talk about what's inside a black hole. Please.
Hello, everybody. Thank you for the invitation. Um, can you see my mouse?
Yes.
Okay, so this is the name of my university in Hebrew. So I'm just putting it on to remind people that English is not my language. I'm sure that you can sympathize with that. Okay, so today I would like to ask a question and try to answer it. And the question is the title, what's inside a black hole? And I mean by that, what's inside the real astrophysical black hole, large black hole. The talk will be very theoretical, but the idea is that I would like to describe the state of a black hole. And as we agreed with the organizers, you feel free to ask a question. I cannot see you at this point, so you just, when you would like to ask a question, just speak up. The work that I will describe is based on many papers that started from about 2015 with my collaborators. My main collaborator is Professor Joy Medved from Rhodes University, and you can see here the name of the other collaborators, most of them students. So let me go back to my question. The question here is what's inside a large black hole, large astrophysical black hole? And one question that many times people have in mind is that we will never know because the black hole has a horizon, it's opaque from the outside, and therefore we can't tell. But what I would like to supply as an answer is that it's made of specific form of exotic matter. And then you can ask me, how can we tell if this answer is correct? And the answer is that because of the recent developments in gravitational wave astronomy, we have a chance of finding out what's inside the black hole or what's the state of the black hole when by the gravitational waves that they are emitted when two or more of these black holes collide. I don't think I will have time to speak about it today, but if you ask me about it after the talk ends, I'm happy to tell you. If we have time, I will discuss it a little bit. Okay, so we go on. And what I would like to show you here is a video of Wheeler talking about what he thinks about the black hole. I hope that the video goes smoothly. Let's see.
For me, very hard to think of parts of the world that are taking part, acting, go to a place where they can't be seen or show anymore. The physical world is one, would be my way to put it. It's, for me, very hard to think of parts of the world that are taking part, acting, go to a place where they can't be seen or show anymore. The physical world is one, would be my way to put it.
So you see, in this case, what Wheeler is actually resisting the idea that when a black hole is formed, this is what he's talking about, there is part of the world or part of the state, as we now say, that we can't access. And this, I share this thinking, and which is very articulated very well by Will. So let me explain what we mean by what I mean by the interior or internal structure of the black hole. And here you can see a visual effect, which is supposed to be a picture of a black hole, but we know now that it's not a picture and it's not a black hole, but still it conveys the idea that you see here, this circle, the black circle, black region. That's what I mean by the black hole. So it's the state of the collapsed matter. And we know that classically it's causally separated from the exterior, but we expect that quantum mechanically this will not be true, that there will be some contact quantum mechanically between the state of the black hole and external observers. So now about quantum mechanics. So I'm sure that many of you share the common expectation that quantum mechanics resolves the black hole singularity. But another part of the common expectation is to expect that the quantum effects quantum gravity effects are relevant only when curvature are at the Planck scale. So what this means is that the classical GR description would change only near the singularity for a large black hole, because for a large black hole, the curvature near the horizon and also formally in the interior of the black hole, it's very small. So if you accept this type of premise, then you reach the conclusion that quantum effects cannot affect horizon scales. There's a scale separation, and the horizon and the singularity are decoupled. What I would like to explain in this talk is that there are quite a few indications that this type of scale separation is not valid, that there is no scale separation, and we should expect quantum effects on horizon scale. I know that this is something that sounds unusual, but let me try to convince you that this is actually the case. So the idea is that if we wish to resolve black hole singularities, we need to accept horizon scale internal quantum structure. And today's talk is about how such horizon scale internal quantum structure can be mimicked by horizon scale modifications to geometry. And a consequence of this idea is that the internal structure of the black hole is expressed in terms of non-relativistic coherent excitations, and because of that, there's a chance of observing some of its internal structure. And this is, as I said, I will not discuss this in detail. I just wanted to flash a slide showing how that internal structure, non-relativistic quote-unquote fluid modes can be in principle observed by a gravitational wave in gravitational wave events. Okay, so I think this is the end of the initial introduction. So maybe I stop here for questions if you have any. If not, we can continue. So the first, again, it's part of the introduction because the actual content of the talk will be in the next section here. So the idea is that if you have a state of maximal entropy on horizon scale, then collapse is prevented, and therefore the singularity is resolved. And this is, if you wish, so a way to express this idea or a way to realize this idea is to look at the state of highly excited string. Highly excited means strings near the Hagedorn temperature, near the string scale, closed strings. So this started by myself and Joy Medved in 2016 under the name polymer model. I will show you what it means, but you can see here a visual realization or visual demonstration of the idea that you have highly excited strings are typically dominated by long strings. So, and there's a long list of discussions in the literature about the state of highly excited strings. You see here, if you wish, a ball of closed strings of total length L, and then their entropy is approximately L divided by L string. And because you can express their configuration as a random walk, their size is essentially fixed by the length, or by the entropy and energy. If they interact, if the closed string interact, then their size becomes smaller than the random walk scale, which is square root of L in any dimension. And the reason is that in this case, they can cut themselves and become shorter, and therefore their size is decreased. And in fact, you can describe the statistical physics of such objects by the so-called Flory-Higgins theory of polymers. And in this case, the fact that the entropy is not necessarily proportional to the volume. So in this case, it's very common in polymer physics that the entropy is either super extensive or sub-extensive. And the reason in this case that it avoids our prejudice that the entropy scales with the volume is because that prejudice is based on weakly correlated or weakly interacting systems. And in this case, from the point of view of the strings, in spite of the fact that the string coupling is small, the correlations are strong. And in this case, you can get any type of scaling for the entropy, and in particular, you can get entropy area law. In polymers, it needs to have attractive interaction, which in string theory we know is dominating the interaction when the strings are long. So the idea is that the reason why such object cannot collapse is because it has entropy. If it cuts itself, the entropy is decreased exponentially. And so in this case, it simply cannot become smaller when, if you think about the free energy of this object, it's maximized at a certain scale, and it cannot collapse. And so the idea is that in this case, maximal entropy resolves the singularity. The first person who actually thought about that in a cosmological constant was the late Jacob Bekenstein in 1989. And he was thinking about this type of idea when thinking back for our universe, or Friedman, Robertson, Walker universe, and asking about the Big Bang going backwards. The universe becomes hotter and denser. Its entropy in a specific volume increases. And if there is a bound on entropy, the universe cannot be, the Hubble scale cannot be smaller than a certain value. And in this case, you don't get the Big Bang singularity. That was the idea, and we attempted to implement this type of idea in the context of black holes and this ball of string. And the entropy bound that we used was an entropy bound that Gabriele Veneziano and I proposed long time ago. And the advantage of this bound is that I can derive an equation of state from it. And also it includes G Newton, as you see here. The original Bekenstein bound does not include G Newton, so it doesn't apply to gravity, and formally. And the other advantage is that this can be applied to a space like a region of space-time that is bounded by a space-like region, and this cannot be done in other bounds which use null type of entropy bounds. And so in this case, the idea is that each sphere of this object has maximal entropy. And so you see that you get Horizon scale internal structure. The scale of this object is the horizon. It doesn't concentrate in a point or a very small region near the center. And you can, as I said, in this case, you can use a type of effective field theory near the Hagedorn temperature, one that was used recently in talking about winding condensate and black holes in lower dimensions. And the idea is that if you accept the maximal entropy state, then you can derive, using the standard thermodynamic identities, an equation of state which leads to P equal rho in any dimension. And in this case, you see that each sphere is essentially a horizon, so like a Schwarzschild horizon. Gravity in this, depending on how you think about it, is strongly coupled. And it's unclear whether you can describe this type of state using classical geometry. I mean, we did a lot of work about that, but this is not the subject of my talk. It's just part of the introduction. So this type of equation of state and free energy is essentially what we call the collapsed polymer model, because it shares many, it's essentially the same effective free energy that was used by Dejean and others to describe polymers. And the idea is that the bound state of interacting closed string near the Hagedorn temperature has essentially looks from the outside like a black hole, and it is regular. So you can think about it as a neutral fastball or a string star. And you can think about it in, I think it's a very nice picture in this case. So you know that when matter collapses, a star collapses, it goes first to a white dwarf, then in this case, a quantum pressure, Fermi pressure, if you wish, stops it from further collapse. Then it goes, when this quantum pressure cannot hold the matter anymore, it continues to collapse, and then the quantum pressure of Fermi pressure of neutrons holds it from further collapse. And now the idea is that when the quantum pressure or Fermi pressure of neutrons is not enough anymore to hold matter from collapsing, you have another form of universal quantum pressure, string entropy if you wish, that prevents any form of matter from further collapse. And you see the neutron star and the black hole, a black hole of essentially solar mass, are drawn to scale here. The black hole is not much smaller than the neutron star. And the idea is that at that point, it's simply the collapse stops because there is a new universal quantum pressure that prevents it from further collapse. And the price that you pay is that you have to accept that there is some horizon scale structure describing when you describe the state of the black hole. Okay, so again, this is a good time to stop for questions if you have any.
Yes, can I just one question is, would this kind of picture require the Chandrasekhar limit or this TOV limit to be changed? Like, would that somehow change? Like, that would be like maybe a possible experimental prediction?
Yes, and this is actually the subject of my next part.
Okay, let me interrupt you no further.
No, you are absolutely right. Because, yeah, I mean, people were asking me these questions when I was describing it at the time, and that's why we went on. And in fact, it's not the Chandrasekhar limit that we're looking, but it's the Bukdal bound. It's very similar.
All right, very good. Thank you.
Okay, any other questions? Okay, so we continue. But please don't hesitate. It's okay. So now, because it's hard to do calculations with this effective free energy of strings, and it's unclear whether there's a classical geometry and so on, people were asking me, but what is the geometry? And initially I said there is no geometry because gravity is strongly coupled, but it turns out that there's a proxy for the state that does possess a classical geometry. In that case, it needs to be able to evade the singularity theorems. And it turns out that maximal negative pressure on horizon scales is a proxy for maximal entropy on horizon scales. And the model that we described or that we invented to describe this maximal negative pressure on horizon scale is called the frozen star. Frozen star name we chose as a tribute to the name of a black hole that preceded the term black hole. This was the original name of the state of collapsed stars for various reasons. Let me not get into them. So let me describe the frozen star. So the idea is So instead of looking at the singularity theorems, it's actually, this would be a very nice project to show that this maximally negative pressure is the only way to evade the singularity theorems. We know that in cosmological constant, because classical de Sitter is non-singular, but the way that I like to think about the singularity theorem is actually using a physical version that preceded the singularity theorem, Chandrasekhar, or in this case, it's the Buchla bound. So this is a wonderful paper, basically showing that the sphere of fluid, with some reasonable assumptions about the composition of the fluid, cannot be stable before it reaches its own Schwarzschild radius. In fact, at a scale of 9/8 above the Schwarzschild radius, it starts to become unstable. And the way that you prove this is you look at the Einstein equations, and you just see that when the ball of the sphere, the ball of fluid, is smaller than this Buchla radius, the pressure at the center of the ball becomes singular. And so in this case, if that were true, then the idea that you can create a ball of fluid whose size is parametrically close to the Schwarzschild radius could work. But it turns out that there is a hidden assumption in Buchla discussions, and also in others, also in the singularity theorem, that the pressure is positive. And it turns out that if you go to maximally negative radial pressure, radial in this case is because the symmetry of the problem, right? A black hole or a ball of fluid is spherically symmetric, so it's the radial pressure that is playing the role of the pressure. And if maximally negative pressure means that P radial is minus the energy density. And in this case, the Einstein equations, as we'll see soon, require this type of radial dependence. The radius in this case of the ball of fluid is parametrically close to the Schwarzschild radius. And from the outside, this type of highly anisotropic fluid looks exactly like a black hole. And so, I mean, to see this, you can just look at the Einstein equation, parameterize a spherically symmetric static space-time, write the Einstein equations, find out that F and F tilde, so GTT and GRR, inverse GRR, are equal, parameterized by the so-called mass function. And the frozen star model, which is a model of a ball of fluid, anisotropic fluid that is parametrically close to the Schwarzschild radius. This epsilon square was recently bounded by 10 to the minus 22 by Visser and company based on EHT observations. And so this can be extremely small, and the object looks essentially exactly like a Schwarzschild black hole from the outside. its causal structure is actually very different from a classical Schwarzschild black hole. It's stated here. You can see further details in my papers. And in this case, let me summarize the frozen star model, which in fact we found by accident recently that was similar objects were discussed in 1979 and then rediscovered furthermore. And then I will also explain how, in a way, Pilchin discovered it later on. So the idea that this classical geometry with radial pressure equals minus the energy density, and then this goes like 1/r², essentially, leads to a geometry with GTT and GRR extremely small. The radius of this ball of fluid is parametrically close to the Schwarzschild radius, and each sphere looks like a horizon. You see each sphere in this case, so you have, it's essentially mimicking what we had before, where each sphere had maximal entropy and so was almost a horizon. In this case, gravity is weakly coupled, except in the center, and we get a regular classical geometry. It's not quite true because you see here, if you want to match this geometry to a Schwarzschild one, then you have to have some kind of a boundary layer where the density goes from 1/r Schwarzschild square essentially to 0. And also in the center, you have to, this formally is divergent, although the divergence is very mild because the mass in the center is parametrically small. And we actually did that by smoothing. We found that smoothing obeys all the energy conditions, and it's formally we can do it without any problem, unlike many other ideas that for black hole mimickers that require negative energy or stuff like that. It's actually, this actually in the context of the string fluid mode, which I will describe shortly, is an interesting aspect that needs to be understood. Now, it turns out, this we found independently, is that what I described, this type of equation of state, is actually the equation of state of a spherically symmetric collection of rigid string with some constant tension. Which is pictorially visualized here in this type of cartwheel. And it's very easy to see that because in this case, if the tension is constant, then the mass function is linear in the radius. And so in this case, if the mass function is linear in this radius, then it exactly means that each sphere is like a horizon. And a really interesting coincidence, I'm not sure if it has any meaning, is that if we compare the resulting tension and we use weakly coupled string theory to relate alpha prime and G string, we get a G string square that's 1/8 pi. And those of you who were studying string theory know that this is exactly the coupling that needs for strings to realize grand unified theory. It's 1/25. I'm not sure if this has any meaning. It's just an amusing observation. Okay, now this I just realized a few weeks ago after a talk at Princeton, and that's why I guess I'm giving the seminar here, is that this type of state is actually part of string theory, and an interesting part of string theory. And in this case, you can actually, this is something that we missed, and we didn't know what the Lagrangian that describes, or what are the actual microscopic physics that describe this type of fluid, except for the fact that it can be sourced by strings. But it turns out that it represents an actual physical state that occurs in string theory, in real string theory. And that's the endpoint of tachyon condensation, which Phil Jean and collaborators worked out. I only listed here a few work. At that time, it was a very popular study. And the Lagrangian describing this, whose solution is this type of state, is actually very simple. It's a dBi action of an antisymmetric tensor K mu nu. You can think about as an electromagnetic field, plus some kind of constraints, which essentially say that this K mu nu is describing a 2D area element, which is essential for this type of description. And K, in this case, has an electric part and a magnetic part. And our solution is actually the simplest solution which was discussed in this type of context. You see here, you take the electric field, electric flux, to be only in the radial direction. The rest, the magnetic field and the other electric fluxes are vanish. In this case, this action is equal to KTR, so the electric field in the radial, the electric flux in the radial direction. K mu nu is given by a very simple expression, and lo and behold, the radial pressure is equal to minus rho, just calculated. P transverse is 0, and the frozen star model is simply choosing KTR to be 1 minus epsilon square over 8 pi r square. And this reproduces exactly the frozen star model. An interesting aspect here is that you need to smooth the core and the outer layer. And in that case, we know from our calculations that the magnetic field changes. You can see it from the conservation equation. So here the density gets smaller and the magnetic field compensates for that. And here the density approaches the constant, and again the magnetic field changes for that, and it might be related to a field of a magnetic monopole, as some of the literature suggests. And this is something that I'm working on currently, and it's a very nice extension of these old papers. So I'm reading them and trying to understand them. And okay, so as I said, this is the frozen star model. And let me summarize it, the frozen star model, and we can go to questions. So here is the list of papers that we wrote recently about this. And you can see a very nice resemblance the state here is a state of highly excited strings, high entropy. This formally is zero entropy, but of course, if we recently checked that if you apply the Gibbons-Hawking type calculation, this has exactly the black hole entropy, but it's a very interesting resemblance. And I've been toying with the idea that if I take the string fluid and heat it up to the string temperature, this can be done by looking at winding mode condensate, that we get back to this polymer stuff, which is very interesting. By the way, I should have mentioned that in this case, it's an endpoint of tachyon condensation in open strings, but it gives a closed string state. So this is a closed string state, similar to the polymer model that we had. And so in this case, we see that the frozen star is a regular black hole mimicker in the sense that it solves the Einstein equation. It is regular. It has arbitrary compactness. It is black. This I didn't understand, but I didn't explain, but anything that goes into this object essentially never gets out. It gets out, but it gets out after so much time that practically it doesn't get out. It obeys the null energy condition. There are no obvious pathologies. We're still checking for them, but we couldn't find any pathology. And it's ultra stable. I didn't show that, but we will see that in the next stage. And so I think this is a good time to stop for questions.
Have you considered rotation? Maybe like a rotating version of this?
Like my next part?
Oh, okay.
But I don't know if this is significant, but could you go back to this string fluid Lagrangian?
This?
No, yeah, this one. So when we were doing this was from tachyon condensation model. So what happened is you have essentially Dirac-Bonifeld type thing, which is multiplied by a potential that goes to actually zero.
Yes.
And I don't see that coefficient of this dBi going to zero. So I'm a little bit confused. Is it Hamiltonian or action? You are right.
So this I just took from your papers with Gary. So if you go,
Oh, I see. This is a dual picture.
Yes,
I'm
exactly.
sorry. That's right. This is the dual picture. Sorry. Of
Exactly.
course, I have a small section that has dual picture.
Yes, yes.
Yes.
But the dual, you see, the dual picture is the most direct way to compare to our model.
I see.
And in fact, the Hamiltonian picture is very useful to understand the dynamics. But then if we want to present a calculation in a way, to couple it to gravity and write the Einstein equation, T mu nu, and so on, the dual picture is much more useful.
I see. Another question was, you have this parameter epsilon, which is sort of arbitrary thing you put in. Does it sort of relate to anything on the left-hand side of this slide, or is this still again some sort of integration?
No. So in this case, there's a family of solutions, as you pointed out. This theory is in a way it's scale invariant.
Oh, it's merely density then. You
Exactly.
give this particular density. Okay, good.
Yes. So that's actually very important, because to mimic black holes, you have to have black holes at any size, right? So in GR, this is what happens is because the theory is essentially scale invariant. It has a dimensionful coupling, but the dimensional couplings is outside the action. So it behaves as if it's a scale invariant theory. And this theory is also scale invariant, as you pointed out in your paper. And it's in this case, this means that you can have a state of any mass, any size. And this epsilon square is essentially fixing the size or mass, if you wish, of the solution. So it's not a property of the action, it's a property of the family of solutions.
Thank you.
This is actually an important point because many times when you try to modify GR or extend GR, you put in a scale. And when you put in a scale, you get a solution only at one scale. But if you would like to describe black holes, you have to have a theory that has solutions at any scale. And in fact, this is also true for cosmology, but that's for another talk. Okay, so
Can I have one more
yes,
question?
sure.
So the symmetric spherical symmetric picture when you have radial string fluid. As you said, this is supposed to represent, if you take the picture literally, the Lagrangian literally, this is supposed to represent closed string. So it
Yes.
cannot quite end. So
Right,
how should I
right, so-
interpret this, the fact that you have sudden decrease of whatever is effect around the
Okay.
horizon size?
Yes, so this in fact is something that I'm trying to understand right now. I understand it in the mathematics. So what happens is that, where is it? You see here the little dots here, they represent a decrease of the string density, in fact. So I think what happens is that they turn around.
That's
And in fact,
what I thought.
yes, but I cannot prove it. So this is what I'm trying to see. I know that P transverse in my language is responding to this. P transverse corresponds to the magnetic field and probably to the bending of strings, but this is something that I haven't been able to mathematically describe yet, but it's likely that this is what happens. And another interesting phenomenon happens here, right? It's regular here, and also they cannot end here, the strings. So they need to do something interesting in this core region. But I haven't figured out yet what they do. Now with the Lagrangian, then probably it's possible to understand how they bend here and how they bend at the end, which would be very nice.
Thank you.
Any other questions?
I have one more.
Yes.
Is there any some way that this scenario could mimic like a radial infalling observer? Like
Okay.
if he hits the
Yes.
surface, does it create some type of excitation?
Yes.
You know.
Yes. So in fact, this is described in detail in our paper from January this year. So since you asked, let me explain on this picture. So what happens is that when, first of all, a real observer, real physical observer will be essentially shredded as it comes to the horizon if it has a special extent, right, because of the tidal
Right.
forces. But let's think about a photon, okay? So a photon or some massive particle, point particle like a probe particle. It turns out that, and this is also true for Schwarzschild black holes, it has to go in radially. In fact, Samir Mathur used this property to argue about the information paradox and the firewall. But this is a simple consequence of having a large redshift. So it has to go radially, and essentially they have to go along the lines. And because the metric GTT, where is it? You see, GTT is extremely small. The redshift is very large. So in this case, the time that it takes to move on this string is extremely long. So basically what happens is that a probe that falls in, essentially sticks to the surface, and that's it.
Okay.
So that's how you avoid parts of the information paradox. My focus here is on the classical geometry. You can look it up, or if you want, I can explain some more. I have some backup slides at the end of the talk about the motion. It's important. So, okay, so now let me go to the rotating frozen star, which is again a challenge because, as far as I know, this hasn't been possible for other models of a black hole mimicker. So let me start by a quick reminder about the Kerr black hole. So the idea is to construct a rotating version of the frozen star whose exterior geometry will now be Kerr rather than Schwarzschild, and then see what the internal stuff has to be. And so what we do is we start from the Boyer-Lindquist version coordinates of the Kerr geometry. You see here delta is the quantity that when it vanishes, it defines the horizon, r squared plus a squared minus 2mr. A is the dimensional spin parameter of the Kerr black hole. M is its mass. Sigma is g theta theta. It's r squared plus a squared cosine squared theta. And what we did is we went to the zero angular momentum observer coordinates for rotating observer. It turned out to be the simplest way of finding out the geometry, which basically means replacing time with a linear combination of ddt and dd phi. And then in this case, the near horizon geometry of Kerr turns out to be this. So you see if you wish, the GTT, G chi is delta over sigma, and the GRR, inverse GRR, is also delta over sigma. So the structure here is very similar to the near horizon geometry of a Schwarzschild black hole. And the only difference is in the geometry of radial surfaces, which is different now. Instead of being spherically symmetric, it's axially symmetric because this quantity sigma depends on theta. And this is depicted here, this type of, although this is actually misleading. And the rotational velocity frequency of the horizon is a over 2mr plus. R plus is the outer horizon. And another useful quantity is this capital R square, which is r squared plus a squared, which turns out to be the analog in Kerr geometry of the Schwarzschild radial coordinate, in the sense that this is an aerial coordinate in the Kerr. That's how it's defined. And this is also the definition of the radial coordinate in the Schwarzschild geometry. Okay, so you see from this type of metric, we can go to a version of the frozen star. We just set this delta over sigma. So we're approaching the horizon from inside and then just continuing inside with delta over sigma replaced by epsilon square, and leaving the geometry of radial surfaces as the same, as being the same as the geometry of the outer horizon of the KIAS geometry. And in this case, you see that this is regular. The geometry is regular everywhere, except for a region near the center. Here, of course, it needs to be smoothly connected to the KIAS geometry. We haven't done that explicitly yet, but I don't see any problem in doing this. And you see that in this case, the inner horizon is gone, the inner ergosphere is gone, and outside the outer horizon, the geometry is exactly here. So this is our proposal for the rotating frozen star, and we can now check that that it actually satisfies the requirements. So, as I said, in this case, we also get a pure radial trajectories. The symmetries of KIAS geometry are actually preserved. So we have a killing tensor with a Carter constant that actually vanishes in the leading, so it's order epsilon square. So this geometry obeys, it has all the symmetries of the KIAS geometry, so also in the interior of the black hole. And when we calculate the Einstein tensor from the metric, we get again radial E equals minus rho. We can calculate the mass by just integrating the energy density. And actually, it was a big surprise to us because this complicated integral actually integrates to 1. We didn't expect that, but it's a nice coincidence. It has to be this way. And in fact, the mass that we get is the so-called irreducible mass of the KIAS black hole. And this was introduced by Christodoulou a long time ago, and it's accepted as the rest mass, if you wish, of the rotating black hole. And in this case, I will discuss later how you get the full mass by just integrating the first law. And then we can also calculate the angular momentum. In this case, we have to go to a different coordinate system because in the zero angular momentum observer frame, there's no angular momentum. So we have to go back to a rotating frame. And in this case, we found that the T5 component of the Einstein tensor is simply A times the TT component. And so we can relate the angular momentum to the mass, the irreducible mass. And we find that this ratio is exactly the one in the corresponding KIAS geometry. And then by standard arguments, integrating the first law, we get, by including essentially the rotational energy, we get the full mass of the KIAS black hole with the ratio of angular momentum to mass equals to the same one as the KIAS geometry. So in this case, the idea is that what rotates and has the angular momentum is this collection of strings that are rotating. Now, there is another very interesting aspect which I would really love to understand in terms of the strings, and that you see here, I glossed over it. This is the expression for the energy density and pressure that are, one is minus the other, but you see this factor here? It can change sign. So when R is small enough, this changes sign. So formally you get a region of negative energy. That's not a problem because all the observers that can fall in are radially null observers, and so it's the null energy condition that's important. It is satisfied, but what I would like to, and this is the actually a well-known fact about the KIAS geometry, is that it's the Gaussian curvature of radial surfaces near the horizon is changing along the surface from positive here near the equator to negative here near the axis of rotation for spins that are large enough. And in this case, square root of 3/2 is the spin at which this region of negative curvature actually reaches the outer horizon. So for A's that are larger than square root of 3/2, there is a region here of negative curvature, and this is what is, this is why one gets this, because this is actually proportional to the Gaussian curvature of surfaces, of radial surfaces. And another thing that I would like to understand is, in terms of the strings, what is it that they do here? I would expect that they bend around, but I wasn't able in the little time that I had to explore the string Lagrangian to understand how this happens. But this needs to happen. This needs to happen, and I think very interesting, would be very interesting to understand it. Yes, so this is what I was discussing, how this string picture is actually realized in this type of rotating solution. I see here that I'm basically at the hour mark, and I'm not sure what exactly, how I should continue. So should I stop, or should I go on for a few more minutes?
I think, well, you can have, let's say, roughly 10 minutes if you want.
I don't want to pause. It's just that I can stop here, or I can continue on depending on what you usually do, or.
Well, it's quite flexible, so yeah, you can
Okay.
have, let's say, 10 more minutes.
Okay. So you see here that again, as in the static frozen star, this to base essentially all the requirements that you would like from a state that describes, that is sourcing the KIAS geometry. And the next is the stability in internal structure. let me be brief here. It's again, there's a paper, but so let me just show you, which I think also connects very nicely to the papers on the string fluid. So let me go very quickly here, and as I said, if some people want to stay on and ask me questions, I can explain. So let me just go very quickly through the calculation. So in this case, it's an extremely non-isotropic fluid, and when you do perturbation around it, you have to do something that is not the standard perturbation theory, which we did. And the result in this case, let me show you here, is that if P plus rho, so P radial equals minus rho, is kept, the result is that this object is ultra-stable, meaning that you cannot excite this collection of strings in any way. And so if you wish, this was done, this we showed for the static case only, but I expect a similar phenomenon to work for. So if you wish, the PR equals minus rho behaves exactly like a black hole, because black holes cannot be excited, and they're described only in the static case by their mass. And here it's the same, so you cannot excite it. In spite of the fact that you might think that it has an internal structure, it doesn't. It's ultra rigid. The only thing that you can do is increase its mass or decrease its mass. Okay, so now it turns out that if we want to describe an object that is similar to the string state that I described earlier on, and we include interaction, G-string effect in the P equal plus rho, so in the highly excited strings, turns out that in this case, you can actually excite that object. In the G-string equals 0 case, you cannot excite that object. So this is something that I didn't discuss, but it's true. And so in this case, we need to modify the collection, the state, such that it mimics also G-string effect. And the way we do that is by moving away from P equals minus rho. And in this case, moving perturbatively away from P equals minus rho, because the G-string square effects are supposed to be small. And another very interesting question that I'm trying to understand now, and I think I have an answer, but I'm not sure yet, is how to include this type of possibility of exciting the strings using the dual description of the endpoint of tachyon condensation. And in this case, if we just look at the simplest solution where we have only electric flux, you have to have P equals minus rho. And in this case, I know that you cannot have perturbation. So you need to move away from that. And we were able to move away from that using by perturbing the energy momentum tensor. This is in a recent paper that we wrote. And in this case, let me go to the final result for the modes. So you see here, we get a spectrum of non-relativistic modes. This gamma is essentially parameterizing the deviation from P equals minus rho, and it's related to having a transverse pressure. So a hint is that in this case, transverse pressure is related to having a magnetic field. Okay, so we find a non-relativistic modes, which is again what we expected from previously results, and brings me to what I announced in the first state transparency. And because of time, let me just go to essentially my conclusions. So what I described is an idea stating, or premise is that resolving black hole singularities requires horizon scale internal quantum structure. We discussed what this means in practical terms, and that this can be mimicked by a horizon scale modification to the geometry. That's the frozen star model. And I really went fast over the showing that in this case, this internal quantum structure is realized by non-relativistic modes. And let me stop here by showing that. As I expected, we didn't have time to discuss observations, but they are also very interesting. So thank you very much for your attention. I stop here.
Okay, thank you for the inspiring talk, and we have some time to hear some questions from the audience.
Toward the end, when you are going to do stability analysis, I guess the energy momentum that you end up writing, given the geometry, all obeys the positive energy conditions.
The non-energy condition, yes.
All the energy conditions.
Yes, and yes. So in the rotating case, so in the static case, it obeys all the energy conditions. In the rotating case, you know that negative energy is not something that, for example, in the ergosphere, formally, you have negative energy, but that's because you're using the wrong observer, if you wish. So if you use the correct observers, which are null radial infalling observers, in the rotating case, the null energy condition is satisfied, and so there is no obvious problem with energy conditions in any of these models. This was a big, this is something that we worried about in the rotating case for some time, because you see explicitly that you have a region of negative energy, but the resolution is that this is because you cannot have static observers in which are measuring this negative energy in the interior of the black hole. And in the static case, that problem never arises. The energy is positive, the non-energy condition is obeyed. And this is discussed in details in our papers. This actually is an important point, because many of, or most of the attempts to create this type of state, they suffer from this type of pathology. They either need large negative energy, or that or the non-energy condition is not obeyed, and so on. So in that sense, I think the fact that you can get it from a string Lagrangian actually explains why this is so.
Earlier, when you are showing us the shells, basically shells after shells after shells, I was trying to remember what I did when I was a student, this Israel junction condition.
Yes.
So remember, I mean, if I have a massive shell, it's just mass, consists of density and no pressure. Israel junction condition actually tells me how the shell collapses, evolution.
Yes. Absolutely.
So suppose I take your example, your shell with radial pressure equal density.
Yes.
Will you be saying, that even if you have a single thin shell, you end up with
No.
a static configuration? That doesn't happen. Or
No,
you need
no.
all of this.
You need
stacks
all
of
of them. Yes, because otherwise, this is the horizon scale. This is the realization of horizon scales. So, for example, the way to see it is this is really this Mukdal bound. Let me find it. Maybe, where is it?
this 9/8. If
Yes,
you are below
so,
it, you can do this?
No, so where is it?
Yeah, very early on, I thought.
Yes, it's here. I think it's just.
No.
No, it's later here. So this actually is a wonderful paper. Yeah, it's a 4-page paper, and I recommend it. And so you can ask yourself, how can you evade, or if think about the singularity theorem, how can I evade them? So suppose that I just have, as you said, a shell of some thickness with P radial equals minus rho, and then inside I have empty space or some matter. Then what happens is that if you look, there's an integral in this type of setting that determines the pressure. And you can see that if this integral is not going from essentially the core, or r equals 0, to the surface, you cannot evade the bound. And similar in the singularity zone. So PR equals minus rho means that light rays are parallel, right? It's like in the zeta.
Right.
If you think about the Ricciarduri equation, PR equals minus rho is the kernel that goes into the focusing or defocusing of light rays. And so PR equals minus rho means that photons go in parallel. So they don't focus. And the idea is that, and in this case, there's no trapped surface in space-time, because when for finite epsilon square, even for 0, there's only a marginal trapped surface at the horizon, but you never get a trapped surface. So it's a combination, is that you avoid the trapped surface, and then you force geodesics not to focus or to focus very little. And you have to do it all the way parametrically close to the center, otherwise they immediately focus and go single. And you can see it also in this case. Or alternatively, you have a core of some radius with PR equals minus rho and an outer shell with a different equation of state. Again, the theorem works and you cannot have a stable configuration. So you cannot evade the singularity theorem. Has to go all the way.
Sean, maybe Ramy, if I take typical fuzzball scenario for supersymmetric extremal version, and you have again this ball of some things, and suppose you average over and ask about this average energy momentum tensor, is it going to look something like this, or would it be very different?
So, that's actually some people. So first of all, the difference here is that this is neutron, right?
Right.
So,
of course, I do realize that, but just the
yes.
energy momentum.
Now, yes, and the other thing is that the really accessible fuzzball calculations are for extremal or near extremal solutions.
Mhm.
It's only this, the rotating paper is from October.
Mm.
And so it's only in the rotating paper that we can go to the extremal limits, right?
Right.
And one very interesting question would be to see if I go to the extremal limit in the rotating case, and I go to a version of the fastball solutions that is experiment with rotation rather than with charge. This can be done.
Right.
What is the connection? And obviously, I'm not expecting a simple relation between a single fastball geometry and our model. It has to be some kind of averaging, but I'm not sure what it is. But it's a very interesting aspect of, I mean, it should be very interesting to find out what is this relation. That's why having the rotating solution is crucial for this.
Yeah, I think yeah, averaging, that's a good, very good question in this fuzzball with these microstates. What do they average to? Yeah.
Yes, and well, we can probably do a charge, but I think it's enough to consider the rotating case.
Right.
Mm. Mm.
But I mean, in the rotating case, I didn't quite catch the equation of state there.
It's
Was
PR
it
equals
substantially
minus
different?
no, it's exactly PR equals minus rho.
Oh, okay. In that case, oh, I see. So it's really more of fuzzball side. What do they know about the effective sort of average?
Yeah, so that's
momentum.
why I'm expecting something like your model to be able to realize the real, right? Because PR equals minus rho is something that I can describe with the dual Lagrangian. But
I mean,
and the
after all
challenge
this
is,
tachyon condensation we did, one of the sort of, I mean, simplest version of it is sort of D-brane, anti-D-brane collision. I mean, D-brane,
yes,
anti-brane annihilation, tachyon condensation thereof. And the thing we wanted to see is closed string theory emerging out of that. And people try to use that as a neutral black hole model.
yes.
And
And
there,
you did you know specific papers where this was done?
I mean, I should try to find out. There was one paper about 15 years ago. I think it was somebody from Sweden or something. And no, they didn't do any real computation. All they did is try to find scalings. I mean, it's not like they are writing down solution. It's more like trying to put D-branes on torus and anti-D-brane on the same place and ask about thermodynamics, basically. And there was reasonable scaling behavior. That was all.
So maybe it was Wolf, maybe it was Wolf Danielson, but I will check.
It could be Wolf. Yes.
But this, what you said is that I think some of the recent development in fastball description is in fact using this type of blown up D-branes and so on. It's very hard to follow. I'm sure that Sean knows more about it. Yosef and others were doing that, but in this case, you see the type of geometry and models that I described are so simple that you can actually try and decide what the conclusions are. And the typical fastball models that go towards the neutral solutions are extremely complicated, and it's very hard to realize. That's why it would be very interesting to see if if it's possible to show that this is somehow this effective description of the fastball model, the neutral fastball model, this would be really great because it would really establish this type of connection in a nice way. But
yeah, I think Pierre and Ibu, they recently wrote down, I think, some Schwarzschild, like kind of from a different angle, but a neutral Schwarzschild like smooth solution. So you'd be interested to see what the connection was there in this.
The thing is that I really tried, and I also discussed and with Joseph and so on, and it was, the level of complication was so high that it was hard for me to tell.
Yeah, it is quite complicated because you have a lot of stuff, different cycles shrinking and not shrinking, and the net effect is something smooth, but yeah, it's quite a bit of components to those solutions. Yeah.
Right. So it's hard to tell what is essential and what is less essential. And here, the nice thing about this type of stuff that I was describing, that it's extremely simple, and it obeys essentially all the constraints that we wish to have. So
I was very surprised that you did the stability analysis as well. I sort of expected, having a solution like this could be written down once you write the metric. But of course, always the problem is stability, and you are saying that there is no stability issue.
Yeah, but I think in your paper, in your 04 paper, you also did the stability analysis, which is not that different from what we did. And in fact, I think that having either magnetic field or tachyon matter corresponds to this change away from PR equals minus rho.
Oh, yes, yes.
And yes, so I think.
But that brings up, the other question you didn't say much about Hagedorn temperature other than the earlier introductory motivation. But if I take this string, maybe I don't understand Hagedorn limit that well. You are saying in the Hagedorn limit is dominated by long string.
Yeah, this is a well-established fact. And the reason is because their entropy, this I can explain very easily if this is what your question about. So just think about free closed string near the Hagedorn temperature. What happens is that its entropy and energy are essentially equal in string units. This is a well-known classical computation of string theory, because the entropy is proportional to the length, and the energy is, because its tension is proportional to the length. Okay, now, so think about one closed string, okay? One closed string. Now, ask yourself now whether two strings with the same size, with the same total length, compare them to one string with the same total length. The entropy of the longer string is exponentially larger than the entropy of two strings, because it goes like L factorial. This is very nicely explained in these old papers by, I didn't list all of them, but it's very nicely explained in these classic papers about the Hagedorn temperature. And the key is that the entropy and the energy are essentially equal. So you cannot just use standard Boltzmann type scaling. You have to take into account this free energy, and the free energy, the entropy and the energy are essentially equally important.
I guess the confusion I have with this, yeah, in long string in that sense, I do understand. But this is like in this picture, it goes essentially everywhere, bending and winding. And
This is
whether
also, yes, this is also
average
well
over
known.
this, would I get pressure, radial pressure big enough for your picture? I guess that's the part I don't see.
Yes, so to
Maybe
do
you don't
that,
want that.
no. I actually do want that,
You
but
do want that.
to get that, you have to include interactions. So
I
the
see.
free strings doesn't have, it's too big, right? It's if it's free string, then it scales like the random walk scale, square root of n. And to get to a black hole, it needs to be smaller, because in this case, the entropy is R squared. So you need to allow interactions, and this is discussed by this paper and also Atiquita. We discussed that there. We wrote 2 papers about that, but the main paper is the one from, it's called the Emergence of Horizon or something like that. It's from 2016. I can send you the reference.
Yes, please.
Right. So in this case, it needs to be able to interact, to cut itself, and then there is a distribution of long strings, but it's essentially a logarithmic distribution, and I may have it somewhere, but never mind. So, and then to get to the radial to P equals rho, you need this, essentially you need the string to be within its Schwarzschild radius, which in this case requires you can have it with weakly coupled strings, but you have to allow, in this case, you have to allow them to be near the Hackelott temperature. So this I didn't explain very, because it was part of my introduction. It wasn't my emphasis, but this is actually a very interesting aspect.
I have to go. I have a meeting with
no
president.
Completely
Maybe between 2 of us, like Thursday same time or Friday same time, whichever fits.
Okay, let me check my schedule, and then I will write